let us discuss what is a singular point of a complex function. If a function fails to be analytic at z0, but it is analytic at some point in every neighborhood of z0, okay, then this z0 is called singular point or singularity of f. So you take z0 and you take a neighborhood around z0. So now there exists a point z1 at which the function is analytic, but at z0 it is not analytic. So let us write here f is not analytic at z0, but there exists a point z1 which belongs to any neighborhood. So any neighborhood of delta, this is how I am going to write n delta of z0. Any neighborhood of z0 can be written like this. There exists a point in every neighborhood such that f of z is analytic, or in other words f is analytic at z1. Okay. Now let us take this function. So the first example, f of z equal to 1 by z minus 1. You can see that z is analytic everywhere except at z equal to 1. Therefore, z equal to 1 is the only singular point of f. Okay. Suppose if I take another function, let's say f of z equal to z square plus 2z plus 1 by, I'll take z into z minus 1. You can see that singularities of f are, one is 0, z equal to 0 and z equal to 1. You just need to see where the denominator is getting 0. So denominator is getting 0 at z equal to 0 and z equal to 1. Okay. Whereas if I take another function, let's say f of z equal to real part of z. And what do you know about this function? This function is nowhere analytic. Why? Because it is not differentiable at any point. So we know this is nowhere analytic. So now does it have any singular points? Or can I say that every point in a complex plane is a singular point for this? See the definition and tell me what is the answer. Does this function, real part of z, have any singularity or no? You are saying no singular points. Correct. Why? Because if you want to say a point is singular, we want function to be not analytic at z0, and at the same time in every neighborhood we expect at least one point where it is analytic. But here you know that this function is nowhere analytic, so now it is not possible to find such a point. So what you can say is there is no singularity. No singular points exist for f of z. Okay, but no singular points, it doesn't mean the function is analytic. Suppose if you know that the function is analytic at least at one point, and if you have this information, it has no singular point, then you can conclude then the entire function is going to be analytic. Okay, but here the function is nowhere analytic, so it cannot have singular points. But it doesn't mean, having no singular points, it doesn't mean the function is fully analytic. Okay, so be careful with the definition. And you have some other examples like f of z equal to imaginary part of z. You know this function is nowhere analytic, and also mod z square, this function is also nowhere analytic. Okay, so all these functions comes under this case. Now let us look at some other examples. If I take f of z equal to sine z by z, so what are the singular points of this function? What about the first function? What is the singular point? Okay, you're saying 0 is the singular point. Yes, correct. The singular point is 0. It has only one singular point. And here, what is the singular point for the second case? Even in this case also, the singular point is 0. Even the same thing is true for the other one. So if you look at these three problems, one is sin z by z, another one is sin z by z square, and the next one is sin z by z power 4. All these three functions have the same singular point, which is 0. But all the functions are not same. They are different functions. So definitely these singularities are going to be different. So now how to classify singularities? Like, do you agree that the singularity here will be same as the kind of singularity here? So there you observe z is there in the denominator only once, but here we have it twice. We have it 4 times here for the last one. And you can observe one more thing, that is sin z by z. Sin z, we know what is the expansion of sin z, right? Let me recall the expansions we did in Taylor's for real valued function. So sin x is equal to x minus x cube by 3 factorial plus x power 5 by 5 factorial plus minus and so on. Okay, when you take sin x by x, then you'll get 1 minus x square by 3 factorial plus x power 4 by 5 factorial minus and so on. So now when I write expansion for this, like you take z as x, then you're going to get 1 minus x square by 3 factorial. I mean z square by 3 factorial plus z power 4 by 5 factorial minus and so on. Now you see here in the denominator I am finding z, but if you look at the expansion, there is no 1 by z in the denominator. Now here it appears like we have singularity, because 0 is there in the denominator. But the moment you write expansion, I am not finding any 0 in the denominator. Okay, there is a singularity, but after writing expansion, it seems like no, there is no singularity. Okay, so this kind of singularity we call a removable singularity. Why? Because z equal to 0 is a 0 of sin z. Since it is 0 of sin z, then this 0 on the numerator and the 0 in the denominator will get cancelled. So this is the expansion you get. Okay, whereas here when it comes to here sin z by z square, so 1 by z will come, so 1 by z minus z by 3 factorial plus z power 3 by 5 factorial minus and so on. You see here we are seeing z square, but 1 by z is there in this term, in the expansion term. Okay, so we have a singularity. And if you look at the power of 1 by z, you have 1. And this singularity has a name. It is called simple pole, pole of order 1. Anyway, we detailedly classify all these singularities later on, but now right now I'm just giving you an idea. Okay, and when it comes to the other case, sin z by z power 4, so what you can expect is 1 by z cube, that is the 1 by z term with highest power. That's what I can expect. And the next is going to be you may find z power z. Okay, so now this is going to be a pole of order 3. This is also a singularity, and this singularity is nothing but pole of order 3. Okay, so now you can have some other expansions. Let us say if I take sine of 1 by z, this time I'll start with f of z equal to sine of 1 by z. So here also the singularity is 0 only. singularity is 0. But when you look at the expansion of this, you'll get 1 by z minus 1 by 3 factorial into 1 by z whole cube plus 1 by 5 factorial into 1 by z whole power 5 plus and so on. So if you look at the highest power of 1 by z, there is no end. It is going till infinite. It means we have infinitely many terms which have this term 1 by z. But if you look at the other cases, it is different. There is no term which involves 1 by z in the first case, in the fourth example. And next we have only one term, that is 1 by z power 1. And next we have 1 by z cube, that is the highest power of 1 by z. But when you look at the highest power of 1 by z, there is no end, it is keep on going. Okay. So now this kind of singularity we call essential singularity. Okay, so the singularity is classified into three types. One is a removable singularity, another one is a pole of order 1 or pole of order k. It depends on the highest power of 1 by z. If you have 1 by z power k, if it is the highest power, then we say it is a pole of order k. So if there are infinitely many terms which involves 1 by z, then we say it is an essential singularity. Okay, so this is how a singular point is classified. But here I am writing some expansions, but I am not giving any justification. Like from real variable, I am simply saying that from real variable we take these expansions. But I cannot simply say that. We should give some justification. Right? So is it possible to write an expansion of sine 1 by z in this way? Okay, if you write an expansion, what is the guarantee that this expansion sum will be equal to sine of 1 by z? So whenever you write an expansion, you should make sure about its validity, and also you should make sure about its convergence. Is it guaranteed that this sum will converge to sine 1 by z? If so, in which region it is convergent? Is it convergent for all z or for some particular z? I mean, we know about 1 by 1 minus x, right? This has an expansion summation x power n. We know this expansion is valid if and only if mod x is strictly less than 1. In other words, when minus 1 is less than x less than 1. It means the validity of this summation is in between these two only. This summation converges to 1 by 1 minus x when x value lies between minus 1 and 1. So similarly, I am writing some summations here in terms of z. So what is the guarantee that it converges to that summation? And if it converges, what is its validity? Okay, so this is what we need to know. Now, Tylers will help us to get these things, Tylers and as well as Laurent. So now let us see what is a Taylor series expansion of a function. And let's look at the Taylor's theorem. And this is the Taylor's theorem. And see what it says. When you have a function f which is analytic throughout this open disk, an open disk was constructed here. So this f is analytic throughout this open disk. Then if f of z has a power series representation centered at z0, then definitely this coefficient an must be equal to nth derivative at z0 by n factorial. Okay, this is same as whatever we have studied in real analysis case. So now if you want to prove this result, you can do one thing. First you write a series expansion and you try to find out what is a0, a1, a2, a3 and all. It is easy to find them. For example, if I assume this expansion first, f of z equal to a0 plus a1 into z minus z0 plus a2 by 2 factorial into z minus z0 whole square plus and so on. If I plug in z equal to z0, I am going to get f of z0 equal to a0. So I'll get a0. a0 is nothing but f of z0. And if you want a1, do one thing, differentiate f and substitute z0, then you will exactly get a1. a1 will be f dash of z naught. But here you need a assumption. Assumption is that f must be differentiable. Okay, and moreover we are going to take f must be analytic at z naught. The moment f is analytic at z naught, then you can say that f dash exists, f second derivative exists, f third derivative exists. From Cauchy integral formula you can derive all these. First derivative, second derivative, third derivative and all. Okay. So it is easy to see how to obtain an, but the next part is, so it is claimed here that the series converges to f of z. So whatever series you wrote here, this series converges to f of x when z lies in the stated open disk, where the stated open disk is nothing but, means this says the summation converges to f of z when this is true for every mod z minus z naught is less than r naught. Okay, and try to carefully observe this theorem statement. What are all we need is f needs to be analytic throughout the open disk. Okay, when you can construct an open disk around a point at which the function is analytic, then I can write a Taylor series expansion for this function. Now you tell me one thing. Suppose if I start with a function which is f of z equal to 1 by z minus 3. Now my question is it possible to find Taylor series expansion of f of z about z equal to 2, and I took z equal to 2 and the open disk now is z minus 2 which is less than 2. Yeah, tell me this. Is it possible to find a Taylor series expansion of f of z about z equal to 2, and that Taylor series should valid in this region, that is when mod z minus 2 is less than 2? What is your answer? మా ఇచ్చిన ఫంక్షన్కి 2 దగ్గర సెంటర్ చేసి నేను టైలర్ సిరీస్ ఎక్స్పాన్షన్ రాయాలనుకుంటున్నా. ఆ సిరీస్ ఎక్స్పాన్షన్ అనేది ఇక్కడ ఇచ్చిన రీజియన్లో వ్యాలిడ్ అవ్వాలి అని అనుకుంటున్నాను. అంటే mod z minus 2 less than 2 ఉన్నప్పుడు ఆ సిరీస్ ఎక్స్పాన్షన్ వ్యాలిడ్ అవ్వాలి. సో ఆ రెండు కండిషన్స్ సాటిస్ఫై అయ్యేటట్టు సిరీస్ ఎక్స్పాన్షన్ ఫైండ్ అవుట్ చేయగలవా లేదా? వాట్ డూ యూ థింక్? So you are saying it is possible. Are you sure? It means whatever open disk you are taking, in that open disk the function must be analytic. So are you sure that the function is analytic in the open disk which is given there? This is the open disk. The open disk here is this.
Sir, at point 3 the given function is singular, sir.
Yes. So the singularity of f is 3, correct? So if the singularity is 3, then does that 3 lies in this open disk or outside the open disk?
Lies inside, sir.
Lies inside. Then how it is possible? It is not satisfying the statement of Taylor's theorem. No, we want f to be analytic throughout that open disk, but it is not. Because you see, let me say this is z equal to 1, 2, 3, okay, and this is 2. So now I'm constructing a circle with radius 2 centered at 2. So z equal to 3 which lies inside. Now this open disk contains a singularity. Now I cannot say this f of z is analytic throughout the open disk. No. So now answer to this question is it is not possible. Why? Because the open disk contains a singular point. Now can you make some changes so that it is possible to write a Taylor series expansion about 2? Now let me change my question. So the function is same. Now I'm taking the point z equal to 2 and the open disk is mod z minus 2 is less than, let me write r here. So can you tell me what is the r so that it is possible to write Taylor series expansion of the function? What must be r? Do you have any restriction on r, or is it allowed to take any r?
R excluded from point 3, sir.
No, be careful. Okay, let me explain you. See, whatever neighborhood you consider around z0, we want the function to be analytic. Okay, so whenever you are constructing a neighborhood, you should make sure that do not include any singular point. Okay, so suppose if I take a neighborhood of this radius, very small radius, this neighborhood doesn't involve the point 3, so it is possible. So even if I take this neighborhood, yes, it is possible. Why? Because it doesn't involve 3. But if I take a neighborhood here, then it is not possible to write a Taylor series expansion. Why? Because z equal to 3 is included. So what you have to do is, you have to exclude this point. So you try to construct a neighborhood in such a way that which does not include the point 3. It means what must be the radius of the neighborhood. So for that you do one thing. You see the distance between the center of the neighborhood and the singular point. What is the distance? This distance is 1. So when the distance is 1, so you construct a neighborhood such that whose radius is strictly less than 1. Okay, so you try to start with any r. This r is strictly less than 1. So then it is possible to write a Taylor series expansion. Okay, so if r is less than 1, then we can write Taylor series expansion in this region. Okay, in other words, the Taylor series, whatever you have written there, which is convergent to the given function in this region only, when mod z minus 2 is less than 1. Okay, now let me ask you one more question. Now my function is f of z equal to 1 by z minus 1 into z minus 3. This is my function. Now I'd like to think about Taylor series expansion of f of z about z equal to 2. Okay, you may ask me, sir, why are you taking z equal to 2 every time? Okay, let me take z equal to 0. Now tell me, what is the maximum radius of the open disk?
Less than 1, sir.
Less than 1? Yes. Why? Because first you take the imaginary and real axis and you look at the center. We want a series expansion about 0. 0 is here, and next 1 is here, next 3 is here. Now you need to construct a circle around z0 which do not include any singular point. So the maximum radius, it can be less than 1. Even I cannot say it is 1. When it is strictly less than 1, then you can say that the Taylor series expansion will be valid about 0. Okay, so maximum possible radius, it means the maximum possible open disk, you can take mod z minus 1, which is less than r, and r is less than 1. Sorry, it is actually centered at z equal to 0. So mod z minus 0. Okay, now my question is different. This time I am not centering at z equal to 0. Now let me change the center. I am changing it to z equal to 3 plus 4i. Now the center of the open disk is 3 plus 4i. So I'd like to write expansion of f of z, which is centered at 3 plus 4i. So 3 plus 4i, it means somewhere here. So can you tell me what is the maximum possible radius? Let me call it as Rm, upper bound of the maximum possible radius, least upper bound. So all that you need to do is you just take z minus of 3 plus 4i. Okay, Now you see the distance from the center to the two singularities. One singularity is 1 and another singularity is 3. So suppose if I substitute 3 here, when I plug in z equal to 3, then 3 minus of 3 plus 4i, and its absolute value is nothing but 4. So when I substitute z equal to 0, so this is 0 minus of 3 plus 4i, and what is its absolute value? The square root of 9 plus 16, which is root 25, so this is 5. So the maximum, the distance from 3 is 4 and the distance from 0 is 5. So what is the maximum possible radius? What is the maximum possible radius so that no singularity comes in that open disk? So what it must be? Is it 4 or 5? ఇప్పుడు నాకు ఓపెన్ డిస్క్లోకి సింగులారిటీ రాకుండా ఉండాలంటే ఆ సర్కిల్ రేడియస్ ఎంత అవ్వాలమ్మా? 4 తీసుకోవచ్చా లేదు 5 తీసుకోవచ్చా?
Yes, sir. 4, sir.
Only 4, right? If I take 4, then 1 will not come, 3 will not come. You take any number which is less than 4. Now let us do one thing. So far we have seen the validity of the expansion. If you write an expansion, like what is the maximum possible region in which we can write the Taylor series expansion? That is what we saw now. Now let us try to write the expansions in the given region, and let us also write the validity of that expansion as well. Okay. So before that, let me recall few expansions from the real variable case. One is 1 by 1 minus x, which is 1 plus x square plus x cube plus and so on. And another expansion is sin x, which is x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial plus and so on. And the other expansion is cos x, 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus and so on. And then e power x is 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. So these are the expansions we know from real valued functions. Now let us take the expansions of the same function, like 1 by 1 minus z in complex plane, and similarly sin z, cos z, and e power z. You can simply take z in place of x. Why? Because the derivative of sin z, which is same as cos z. So if you take f dash of 0, f second derivative at 0, third derivative at 0, you'll get the same values as sin x. Okay. So what you can do is you can simply replace z in place of x. But here you should make sure what is the validity of these expansions. You try to observe the first series is centered at 0. Okay. And what is the singularity of this function? What is the singularity of this function?
1, sir.
1 is the singularity. Now the distance from the center to the singularity, that is also 1. Why? Because 1 minus 0 will give you 1. Now I can say that the Taylor series expansion, this is valid only in this region when mod z is less than 1. When mod z is strictly less than 1, there only this expansion is valid. Okay, now you can replace, let me write it here. Now 1 by 1 minus z, it has a series expansion, that is 1 plus z square plus z cube plus and so on, and this is valid only when mod z is strictly less than 1. Or this one you can write it as n equal to 0 to infinite z power n. Next, from this I'd like to write one more. Let us say I'd like to write the expansion of the same function centered at 2. This time not centered at 1. I'd like to write an expansion which is centered at 2. F of z equal to 1 by 1 minus z. Now I need an expansion centered at 2, so what I'll do is I'll write this 1 minus of, in place of z I'll write z minus 2 plus 2. I'll add and subtract 2. Now this one 1 by z minus 2 you leave it like that, and plus 2 you take it out, so what do you get here? Negative 2 plus 1, so negative 1 minus z minus 2. Okay, here I got minus 1. Finally you can take minus common. Let me do one thing. Instead of finding the series expansion at z equal to minus 2, let me find it at z equal to plus 2, so that no need of taking this out. So I'll write plus here, then I'll write minus here. So minus into minus plus, this will give me 3 minus z. I'll do one thing, I'll take 3 common. This will become 1 minus of z minus 2 by 3, z plus. Okay, now it is in this form 1 by 1 minus x, where x is nothing but z plus 2 by 3. Now the required series expansion is 1 by 3 into summation n equal to 0 to infinite. In place of z you have z plus 2 by 3 whole power n. Now this is the series expansion centered at z equal to negative 2. Okay, now if you ask me what is the validity of this series, tell me. When mod z plus 2 which is less than, what is it I need to write? Tell me, what is that question mark? Now the radius of the open disk is nothing but the distance between the nearest singularity and the center. Anyway, the function has only one singularity, that is z equal to 1. So what is the distance between z equal to 1 and z equal to negative 2? Be careful, the center of this neighborhood is negative 2. Okay, so what is the distance between negative 2 and the positive 1? Yeah, what is the distance between minus 2 and plus 1?
3, sir.
3, that's it. So the maximum possible radius here is 3. So this expansion is valid and it is 3. Okay, and of course you can see it is in the form of mod x power n, x power n. You know this geometric series is convergent if and only if mod x is strictly less than 1. It means mod z plus 2 by 3 is strictly less than 1. It is same as mod z plus 2 is strictly less than 3. You can directly obtain from here, or you can obtain from the singularity as well. Okay, so next let me think about the rest. Sin x, cos x, e power x. And what do you know about this function sin z? Is it analytic everywhere, or does it have any singularities? Is sin z an analytic function?
Yes, sir.
And it is analytic everywhere, right? It is an entire function. So when it is an entire function, there is no singularity. It means whatever expansion you write here, this is valid for every x. If you see that as a real valued function, we say for every x belongs to R. And you see that as a complex valued function, for every z belongs to R. So sin z equal to z minus z cube by 3 factorial plus. So this expansion is valid for every mod z less than infinite. It means it is valid on the entire complex plane. It is MS saying that z belongs to C. Okay. Similarly, we know that cos z is an entire function because it is analytic everywhere. Therefore, this expansion converges to cos z for every z in the complex plane. So if you ask me what is the radius of convergence, the radius of convergence is infinite here. Whereas in the earlier case, here the radius of convergence is 1, whereas here the radius of convergence is 3. Okay, the radius of convergence is nothing but the maximum possible radius at which the series is convergent. Next, similarly, e power z expansion is 1 plus z square by 2 factorial plus z cube by 3 factorial plus and so on. This is convergent for every z belongs to C. Therefore, the radius of convergence here is infinite. Okay. You tell me one thing. Suppose if I give you f of z equal to z plus 1 by z minus 2. This is the given function. Okay. And given that f of z was expressed in this form, summation n equal to 0 to infinite a n into z plus 5 whole power n. So this is the Taylor series expansion of f of z centered at z equal to negative 5. Now the question is, what is the radius of convergence? So first you do one thing, you try to recognize what is the center of the power series, and you see what are the singular points. And if you see the distance between the singular points and the center, and if you take the minimum distance, that will be our radius of convergence.
7, sir.
You're saying 7. Okay. So let me see. The center of the power series is negative 5. Why? Because you can see z plus 5 whole power n you have, and you equate z plus 5 to 0 and z equal to negative 5. This will be the center. Okay. And the only singular points of the given function is 2. Now I need to see the distance between the negative 5 and 2. So the distance between them is negative 5, negative 2, which is nothing but absolute value of negative 7, which is 7. This distance cannot be negative, so we take the positive value, 7. So therefore, the radius of the convergence is nothing but 7. Okay. Without writing power series expansions, we can tell what is the radius of convergence if the power series expansion exists. All that you need to see is just where are the singularities and what are the singularities, and what is the distance between the center of the power series and the singularities. So the minimum distance is going to be the radius of convergence. Now you do one thing, I'll give you a task. Here I'm telling you that the power series expansion of f of z is this, where an into z plus 5 whole power n, where this an is unknown, no? So you try to find out this an. Find an. Take it as homework. And if you cannot give a generalized formula, at least you tell me, I hope you can give a generalized formula, at least you tell me what is a0, a1, a2, a3, and also I need a15. Or if you feel a15 is very far, let me give a10. Okay. You can always take help of this expansion 1 by 1 minus z and as well as 1 by 1 plus z. You can make use of these expansions and do some modifications here, and you get this form, summation an into z plus 5 whole power n. So take it as a homework and try this. So we'll anyway I'll explain this problem tomorrow, but you please try it before that. Okay. So I'll stop it here and let me know if you have any questions or doubts. Seems no questions. Okay, we'll meet in the next class. Bye.